All right, so now we're going to go on to another whole class of recursive problems, and I would say at least half, if not more, of the problems I can think of to put on a test have to do with solving problems on a tree. And trees are really natural for recursion. In fact, if your input's a tree, you probably want to do recursion. All right? So now, I've had the question on tests early in my day, back when I had different format on tests. I would say, okay, define a binary tree, right? And some people would say, every node has 2 children. Well, that tells me I have an infinite graph, right? And then some people would say, every node has 2 children or 0 children, right? But you might have 1 child. And we also want to add in the fact that the left and right matters, right? There's an order there. So I instead like to give a recursive definition. And part of the reason we give a recursive definition is because we're going to be doing recursion on it, right? And because I want to emphasize that I really love the empty tree. All right? So what's a recursive tree? Well, what's a binary tree? A binary tree is either an empty tree, or it's a single node that has a left subtree and it has a right subtree, right? So then you can say, well, why is this whole thing a tree? Well, it's a tree because it's a node with a left and a right, right? And why is this a tree? Because it's a node with a left and a right. And why is this a tree? It's a node with a left and a right, right? And why is this a tree? It's because it's an empty tree, right? Everybody buy that? All right. Now, we're going to write code to do various simple things, like how many nodes are in the tree. All right? So if this is my tree, what do I do in a recursive program?
To the left and right child.
Do what to the left and right child? We have friends, right? We can give our friend any input that's smaller. Well, come on, if the input's a tree, what I give my friend is the subtrees, right? I mean, and what does my left subtree return? The number of nodes, right? What does the right tree return? The number of nodes. And what is my answer? Exactly, right? Get help from my friends, and then my answer is the number on the left plus the number on the right plus 1. Everybody got that? All right, so I'm going to just have a little talk here because so many people get things wrong, that I sort of emphasize the key things that matter here. All right? I think about there as being this wall between me and my friends. Right? My goal is to have a fast algorithm. So in order to have a fast algorithm, I don't go down here. Right? I don't micromanage my friend. I don't think about their tree. I give them their tree. They give me their answer. Right? That's it. Right? The only thing that you know about the left subtree is what your friend gives you. Right? Everybody follow that? So, and I trust my friend to give me what I want. And then how much work do I personally do? Remember the F of the N. F of N, we're here. It's how much work I personally do. And how much work am I personally doing? It has nothing to do with the size of the tree because I'm not looking at the tree. Right? It's a constant amount of work because I get some constant amount of information here, some constant amount of information here. I combine them and send the constant amount of information up. Right? And so in a test, I'm going to tell you the pre and post condition, right? But about half the time, you have to change them, right? So this tells me, the precondition tells me what I'm passing to my friend, and the post condition tells me what's coming back, right? And if I want more communication between me and my friend, then I change the pre and post condition, and I document that on the test, right? And so what will your friend tell you? Well, certainly, friend tells you the answer to whatever the question is you're trying to solve, and maybe if you want, you can get extra information from your friend, right? Right? He can tell you something else. How do you get it? You change the post condition, right? What are we here? Right? And we know nothing about the world, nothing about the left subtree, right subtree, other than what I told you already. Right? You can give the friend more information if you change the precondition, right? Oops. Right? And you know, and of course, if you change the precondition, you have to change what you do with what you return, right? So you also have a box up here, right? What does the box give you? Gives you everything stated in the precondition. And right, you have to return everything stated in your postcondition. Right? Everybody following that? All right. Number of nodes. Oh, what's the base case here? One node. How many think I want one node?
No child. Empty.
You know I love the empty tree. You know I do. Right? So if you make it one node, well, that's great. Are we done? Well, you haven't solved that tree now, right? So I find people don't like the empty tree, and so they have to make much more fancy code, right? They have to say, if I don't have a left guy, but I have a right, then I do this. And if I have a right and not a left, then I do this. If I have both a left and a right, then I do that, right? You've seen code like that? Right? Here we don't have to worry about if every node has a left and a right child, right? So you just have to know what the answer is for the empty tree, right? So better base case. Everybody following that? This, we're going to do one example where the base case is not the empty tree, but generally it's the empty tree. All right? Do we still need that as a base case? No, right? Because the number of nodes in this tree is 0 plus 0 plus 1, right? You have to check those various things work. All right, this is just what I said already, and here's the code. Everybody good with the code? I'm just saying if it's the empty tree, and right, so if you're actually writing real code, you have to figure out what that means. Probably tree is a pointer, and so the pointer is probably nil, right? Then the result is 0, and otherwise you recurse on the left subtree, and you can use whatever notation you want here, right? If you want to say tree.left, tree.right, whatever, right? I actually wrote these slides before we switched over to Java, so, but anyway, it's pseudocode. Everybody good with that? So now when you're thinking about whether your program works, what I like to do is I like it to work. I write it thinking I have a general left and a general big left subtree and right subtree, right? And I write it to make sure it works. And then I check, does it work in this case? Does it work in this case? And that helps me, in fact, decide what answer I want here, right? It might not be clear what answer I want for the empty tree, but then I make the answer for the empty tree so that this works, right?
Can you go back a few slides? I just put the code one right now. Okay, we're good.
Right.
So for the plus one,
Uh-huh.
on the previous slide, you have here plus one.
Yep.
Oh, that makes sense.
Right. Everybody good? Right, so here we're just testing the various things, right? I write the generic code, right? Then I think, when I'm trying to write the base case, I do it a couple things, right? I think, oh, what would my answer be for the empty tree? And sometimes I get it wrong. So then you check this for two reasons you check this. One, you want to make sure that it gets the right answer for this kind of thing. But it also helps to get your intuition what the empty tree should be. Right? You check it that it works in all these cases. Everybody good? You try the same code, and generally it works. Right? Right, okay. Now, we did all this log A, log B stuff to get the running time. Is this going to work here? Why wouldn't it work? Right, so here we could go through it and we could say, well, I have two friends, and is each friend given half the input?
No, not necessarily.
Right, when not?
When the left subtree is bigger than the right.
Right. Here, we don't know that the tree is balanced. Right? So this works great. This is great to say, oh, look at it, it's order the number of nodes, but that's assuming your tree is balanced. So we're going to do some more sort of thinking, right? Here, what we're really doing is it's the recurse on this whatever size the left subtree has and the right subtree has, right? But we don't know. So, yep.
I was just wondering, I'm still confused about the C. What does the C represent?
C is the amount of work I personally do is into the C.
Okay.
What is the C? If I personally do in work, then C is 1. If I personally do 1 work, then C is 0. All right, so instead we're going to kind of look at the tree of stack frames, right? What we're going to do, what the running time is we're going to do a sum over every stack frame, and we're going to say how much work does that stack frame do. All right? Well, in our code that we have so far, how much work is that stack frame doing? What is it doing? It's 1. It's constant, right? Remember, that was the whole point, is that each stack frame is a constant amount of work, right? So 1 stack frame. Oh, so now you have to kind of say how many stack frames do we have, right? And if this is our tree, then as you can imagine, the tree of stack frames is going to completely mirror the tree, right? You buy that? Because you're recursing on the left and the right, and they recurse on the left and the right. The tree and the stack frames and the tree are the same, right? Is that true?
Just have a quick question about what was going on previously. Like, we're still talking about our size function, right?
Yeah.
Yes, so why were you saying that it wasn't O of n if it was not balanced?
Oh,
Because it still would...
it will be O of n. We just haven't proved it.
Yeah. Okay.
The proof doesn't work. The answer works.
Yeah. Okay. Cool.
So in order to prove it, we'll talk about the tree of stack frames.
Yeah.
Right? All right, so is this the tree of stack frames?
Yeah.
We got any no's out there?
Well, the stack frame will have an empty.
Yes. We got to hang the empties off, right? Yeah.
I have how do we know?
How do we know
The stack frame.
the tree of stack frames? Well, right, this is my stack frame that's given this whole tree, right? So, and what does my stack frame do? It pays attention to the root node. And then I have two friends. Here's my left child and my right child, and they kind of pay attention to their roots. So kind of by induction, the trees are the same, and everybody's paying attention to their root. Right? Each person only deals with their own root, and there's one person assigned to every root. Right? So that's why you get this tree. Does that make sense?
Yeah, so technically they're the same.
Except for the empty trees. Right? You take the tree, And then you hang off the empty trees, and then we get the tree of stack frames, right? And then we have to say, well, how many empty trees are there? Well, it's not more than twice the number of nodes, right? In fact, it's going to be one more than the number of nodes, right? So the number of stack frames is order n, and we already said that the work at each stack frame should be a constant, and so we have order n. Right, everybody good? See, it's the same statement, just a slightly different proof. Right, everybody good? Yeah.
Why is it one more than the number?
Proof by induction. Exercise to prove by induction that in every tree, right? I mean, if this is the tree, right, you got one of those and you got two of those.
Well, like, aren't there more nodes?
Yeah, try it by induction. It's kind of fun. But I'm happy for you to say that it's at most twice the number of nodes, right? Because each node only has, each leaf has at most two. We just need its order n. If you want to know that it's one more than the number of nodes, it's an exercise by induction. Yeah?
Is that order and the number of bits or size of the tree?
Well, so one of the things that I've sort of tried to say a couple times, but it's not written in any slide, maybe I should add it to a slide, is if the input is 2 or 3 or 4 values, then you need to be anal about the number of bits, right? If the input is a big array of values, then let's not count bits, let's count values, right? So here, the tree, the input is a tree. How many values are there? Well, there's a constant number of values per node. So I say that the size of the input is order n, where n is the number of nodes. Yep?
I just wanted to check my intuition here. So when counting the number of empty trees, you can take any tree and fully unbalance it so that it's one continuous path, and then that results in n leaves on the other side,
Yep.
plus one additional,
Yep.
right?
Yep. That's one example. Exactly. All right, so now, sometimes we're going to get trees that have many children. All right? And now this node doesn't have a left and right tree anymore, like subtrees, right? It has a list of trees. You can ask, if you're talking to this node, you can say, how many children do I have? And here it's going to say 4. How many children does this have? Oh, I have 0 children, right? And now you say, who are my children? Well, these are my 4 children, right? Everybody's got that? And so then, when we're doing, first off, what's the algorithm now? How do I count the number of nodes?
Sum all of them plus 1.
We're going to have a loop. Remember I told you recursive programs never have loops. Well, this is except when we don't know how many recursions we're going to have, how many friends we're going to have. All right? So we ask all our friends for their answers, and we add them up and add 1. Right? So here's the code. If it's an empty tree, the answer is 0. Otherwise, here I'm doing a running sum. Here I'm looping from the number of children I have. Here I'm recursing and adding on the number of children, and then I add 1 more in.
A little bit lost though. Like you saying you're doing loop when we don't know how many childs are there. Like
when you don't know how many friends you're going to have, then you have to loop over all your friends, right? So here we have a loop. I told you loops were bad, but it's because I don't know how many children I'm doing, right? I'm looping over my children.
that's like
Yeah?
So where is the counting happening for each children of their children? Is it in the loop itself?
I trust my friend to give me the answer.
So I just loop and see how many friends I have.
Here I asked how many children do I have? Right? So I'm here looping over right? I'm the top guy. This is me. I say, how many children do I have? I have 5 children. 1, 2, 3, 4, 5, right? And then I loop 1 to 5. And this guy, I ask this guy, right? Here I'm saying, tree child, my first child. How many nodes do you have? It tells me has 18. Right? Does that make sense? Everybody get this? Yeah?
How do you iterate over the weight node?
You don't.
You don't, right?
You're not allowed to iterate over leaf nodes.
Okay, then in this case, the base case would never be.
All right, we're gonna talk about this slide and the next slide. We'll have 2 different ways of handling the base case. But here I'm still doing, if I'm an empty tree, then I have a return.
The empty tree happens when the root is an empty node.
Yeah. Yeah, and so somewhat here, let's do it in the next slide and then see how you like the next slide. All right, so here, just so I had the pattern from before, I put in here, well, if I'm given an empty tree, the answer is 0, right? But you might notice here that the very top guy might give me an empty tree, right? But here when I recurse, I'm never recursing on an empty tree, right? So assuming that the boss doesn't give empty trees are never going to come up, right? Yeah, let me do the next slide, right? Oh, maybe I don't. Maybe the next slide's later. Yeah?
This is not a technical question. I'm wondering what's going on with the loop if n equals n plus number of nodes. Number of nodes getting number of nodes, but each.
Yeah, I'm taking a running sum, right? Here my n is 0, and then I get this friend, so now my ren is 18. And then this guy says,
Okay.
right? It's a running sum, right?
Yeah, because I is going to move up.
Right.
You're going to get from the rest.
All right, so in a later slide, we'll deal with the base case, but I think we're going to deal with running time first. All right, whole base case questions, right? So what do we need it to work for, right? We need it to work for the generic case. It needs to work maybe when I have 1 child. It needs to work when I have no children. Has to work maybe it works when I have the empty tree, right? So you try all of these, right? And the same code is working, right? Right here, what does the code do? I loop over 0 trees, right? So that's why it can be a base case by itself, because I don't have any friends.
There's no empty trees in this algorithm?
Well, we did before, and we're going to talk about that in a minute, right? Here, I could have an empty tree if I want, right? Right here, I'm adding that it only comes up if it's part of the original input, right? So we can eliminate that guy. And here's the code that eliminates him, right? Now, you look at this, and you might panic because it doesn't have a base case, right? Nowhere do I say if, base case. But what are the changes I made? One, I made n equals 1, so it has that we're counting our initial guy. So we didn't have to do n plus 1 here. And then I just loop over how many friends I have, right? And note, when does this stop? It stops when you're at a leaf that has no friends, has no children, right? Then this doesn't loop. And it naturally returns 1.
We're just assuming with this code just that the loop specifically is something that increments. So if we're starting with a number of children being 0, it's not going to go like 1 and then down to 0.
No. In me, if I'm going from 1 to 0, then that's 0 iterations.
Done. Yeah.
1 to 1 is 1 iteration. 1 to 0 is done.
Yeah. Okay.
Yeah.
Why there's no base case?
Well, because, let's look at a tree. Right? This guy is going to call all its children. Now, what's this guy going to do? It's going to call all its children, which is nothing. And it's going to return what? It's going to return 1. Right? So this guy is going to return 4 plus 1 is 5. Does that make sense? Did that answer your questions? I think you had the same sort of concerns, right? All right, so now here's our other tree, and what changes here? Well, we have to bring the tree of stack frames over, right? So the tree of stack frames now mirrors the tree, and we no longer have the empty trees to deal with anymore, so that's a bit of a savings. So does everything go through the way it did before? No. Why not? What's wrong?
Because we have arbitrary friends.
Yeah, so what does that do to us? What's wrong on this slide?
The mess up our b values. We don't know how much we're doing each.
Yeah, but we don't. That's not in here.
The coefficient for the beginning.
You were saying that each one of them will do only one?
Right. Here, this is saying each guy does a constant amount of work, right? But this guy here is not doing a constant amount of work. He's summing up over all his friends, and he could have an arbitrary number of friends, right? So that's just saying. All right. So then, if we say how much work he could do, well, he could have order n children, right? So if each person has order n work, and we have order n nodes, then is the running time of this n squared? Shouldn't be. It shouldn't be, right? It should still be order n, right? So, so here, what is the work? The work, we're kind of going over all stack frames of how many subroutine calls there are each time, right? How many friends there are. And I've had various slides trying to explain this, and people have kind of died a number of times, but here we're kind of summing up overall nodes of the tree of, well, how many children we have, right? How much work is this guy doing, right? The corresponding node doing. It's how many children we have, right? So we're sort of summing up overall nodes of the tree of how many edges are coming down from that node, right? And while we can count that in different ways. We can talk about, well, that's then the total number of edges in the tree, right? Everybody kind of buy that the total work is the number of edges in the tree, right? Because we're summing up every node. In fact, this is something that we often do in graph theory. You get an edge. You can think about counting it from here, or we can think about counting it from here. Right, so everybody kind of buy why the total work here is proportional to the number of edges in this graph? Yeah?
Isn't it the same with the number of nodes? What is the difference?
Well, we haven't gotten there yet. Right? Right now, what we're doing is the work is the sum of over stack frames of how much work that stack frame does. Right? Well, each stack frame is associated with a node. So we can say how much work is that node doing? The amount of work it's doing is the number of edges leaving it, right? So what are we summing up? Well, each edge gets counted once. It's counted from, right? In fact, we're kind of counting the top end of the edge, right? We're counting it once, so the work is the number of edges in the tree. But now, how many edges are in the tree? Well, let's turn it around. Let's count the bottom end of the edge, right? Each node only has one parent, right? So this is the same as the number of nodes in the tree, which is order n, right? Does that make sense? Now, there was this, in an olden year, the way I try to explain it is sometimes you want to do banking. Right? How much you have to pay for everything, but you can choose who to pay for it. Right? So if I'm paying for the work of looking over all my children, then that's confusing because how much I pay is not a constant. Right? But let me instead charge that to my child. Right? whenever I loop over my children, will charge the loop of me looping over my children to the individual children, right? And then you'll note, well, each person only has one parent, right? So each person is only being charged for that once, right? So that's another kind of way of looking at it. Is everybody kind of following this? Right?
And why do we prove that formally? Is it too hard?
This is good enough. That's not too hard either. I'll tell you what do you need to know here in case you're in a panic. I have had on tests which say, okay, the input's a tree that has arbitrary number of children. Argue to me what the running time is, right? And what I hope you would be able to say is, well, the running time is somewhat the sum over all the stack frames of how much the stack frame works. And yeah, each stack frame may be doing an arbitrary amount of work, right? But the total work is somehow proportional to the number of edges, right? And each child only has one parent. So really make some sort of argument like that as to why the total work is constant, is order n, right? You could say, well, we're going to take the work of this edge, right? This edge is work. Why is it work? Well, he's looping over those edges, right? You take that work and you bring it down here, then everybody's only working a constant amount, right? Somehow you need to put in some argument about to why that's the case. Everybody buy that? Yeah?
Isn't the number of nodes always one greater than the number of edges?
Yeah. And that's because everybody has one parent except for the root, right?
But the root also does work, doesn't it?
Yeah, but here we have a line that says the number of nodes is order the number of edges, right?
Okay.
And the only case that's not true is if I have one node, then this is 1 and this is 0, and don't notice that, right? We slept that under the rug. Right, everybody good? All right. They made me teach 2011, in which you have to do actual object-oriented programming. So these are copied over from there, right? And I don't know what we're supposed to cover here now, right? I mean, there's this crazy thing that you have this object surrounding it, right? So if the whole thing is a tree, but now we don't want to recurse because we don't have a left subtree and a right subtree. Remember when I was starting to teach this, I had to go to Frank and say, Frank, what's going on? He said, no. These things here of type nodes, right? And so what's tree? Tree has a root, which is a pointer to node, or they don't call them pointers, they call them references, right? A reference to a node, and each node has a reference to a left node and a right node, right? So when we're recursing here, we could say that what we're passing is a tree, right? But we're not really passing a tree. We're actually passing a reference to the root, right? Does that make sense? Do you have any thoughts? No? You're good? Everybody kind of follow that? Right? Really, so that when I first had to teach this, I had to figure it out, right? So really, we're not passing a tree. I don't know what all I'm saying here. It's really passing it a pointer to a root. Everybody kind of good with that? That's more than I want to talk about. All right, here. Okay, now we do the sum of the number of nodes, right? So these programs really should be easy to do, right? If you start thinking about the entire tree, then you're going to panic. Trying to think, how do I get the answer? I'm going to panic, right? So really, it's helpful to think I have these walls here. What information, in order for me to get the answer, what information do I need from my left child? What do I need from my right child? How do I return that information? Right? So here, obviously, I get the sum of the left. I get the sum of the right. I add them together, I add my current value. Right? Everybody got that? Yeah?
So, on that test, you're never going to implement that, right?
Implement your friends?
Yeah. So,
It's recursion.
yeah, but I mean, like,
So you're implementing the method. The method
yeah,
Is your friend
yeah.
at the same time as being the thing, right?
But I mean, like, for example, like, get number of nodes.
Oh, okay, no.
Like, you're not gonna. No, okay, we're good. You guys are good.
All right? We'll show you the code when it comes up. I'll show you what kind of thing I want. All right? So here, what's the base case? Well, it can still be the empty node with the answer of 0. Right? So this is the kind of thing I write on a test. And how should you change it? I don't know. I think this is pretty good. If you want to say something slightly more Java-like, you could say tree.write if you want. But that's implying that all I was sort of warning in the previous slide is, well, in case you did take that course, which you all did, not to panic that I'm ignoring all that, right? I know, you know, that tree is actually a pointer to the root, right? But we don't want to get into that because we're not dealing with pointers in this course, right? So somehow you want to say, I recurse on the left subtree and I recurse on the right subtree. So you say whatever notation you want to do that. Right? Everybody good? All right, so we did that, we did that, we did that. Everybody following all this? Now, how do we do the maximum? The maximum number of the maximum value in the tree, right? You take the max of the left and the max of the right, and then it's the max. You take the max of this and this and this, right? Has a very heap feel to it, right? Yeah?
So, I mean, depending on the language, for a lot of these, you could basically just implement a traversal structure and then pass it whatever function you want to be iterating on every single node, right?
You mean that you're going to use some library that's going to traverse your tree for you?
No, like, I mean, I know you can do it in C even, where you just pass it like, I want to do a max function, or I want to do a sum function, and you don't have to keep recreating the same tree traversal, because the traversal is a separate
Well,
function from the
here, you're going to do it this way,
Yeah.
because I haven't learned that. All right, what's your base case? What's the maximum of the empty set? Negative infinity, right? So here, what's the maximum of summing a number of numbers? Is you want to kind of start at 0, right? And why? Because if you start at 0, then you add the next number, you're rolling. Everybody kind of follow that? And if you're doing products, then you want to start with 1, right? And if you're doing and, then, well, you better start with true or else you're going to be false forever, right? If you're doing max, then I prefer negative infinity. Why? Well, 0 works if all your numbers are positive, right? But if your first number is negative 5, then negative infinity helps you move to negative 5, right? Everybody good with that? And this is what I have the code look like, right? No weird traversals. What's the height of the tree? What's the height of this tree? How do I calculate the height of the tree?
Max height of left and right.
Have you taken this course before? No. Yeah, he's right. Yeah. Yeah. Hmm? The height? Yeah, but, yeah, so one is defining what the height is, and we can, it depends on whether we're counting the number of nodes or the number of edges, but, I mean, how do we calculate it, right? We're not allowed to look at the tree. We get the height here and the height there, right? And then, as said, we take the maximum of those and add 1. Right? Everybody buy that?
So why do we need the max to know the height? So 6 is larger than 4, but you said it's 4.
Well, because the height has to do with the depth of the lowest leaf. And the lowest leaf is based on the subtree that's biggest.
I think it's not looking at the values, it's looking at like how many edges.
Right? Here the height, here 1, 2, 3, the height is 3. Here the height's 1, 2, 3, 4. So the height of the whole thing is 5. Good? So now we have to ask, what's the height of the empty tree?
0.
So you're going to want to say 0. All right. What's the height of that tree?
1.
Well, it depends on what you're counting, right? You can be counting nodes or you can be counting edges, right? So you have to know what you're counting. The answer is either 1 or 2, right? And
Is either acceptable or like non-acceptable? Like if we specify like we're counting height of the
if
edges.
I ask this question on a test, I will specify which I want, or I'll give you an example so that you can interpolate, right? So everybody get here that we could say 2 or 1. So what's the height of the empty tree? Well, it's 0 nodes. Yeah, it's 0 nodes, but how many edges is it? Well, we got to say, what do we want, right? We want this guy to have, this one has a height of 0 because it has 0 edges, right? So what answer do we need from them to get an answer here of 0, right? The max of -1 and -1 is -1 plus the 1 gives us as our 0, right? Does that make sense? So I put this example in here to show you that sometimes the answer for the empty tree isn't as self-evident as you want, and you have to roll back to see what you want, right? Everybody buy that? So here's just the code, right? The empty tree is 0 or the empty tree is -1, depending on the definition, whether you're counting. Here I say the example, a tree with 1 node has height 1. Here I say a tree with 1 node has height 0, right? So we know what we're talking about. Right, everybody good? Number of leaves, here's a fun one. Everybody think about this. Let's shout them out too quick. How many leaves do we have? Right? And then think about what the base case is going to be. Think about if there's anything funny happening. Everybody's thinking. Is everybody done thinking? All right, so you get your help from the friend, right? He's going to say he has 3 leaves, and he's going to say he has 2 leaves. What's a leaf, of course? A leaf is somebody who has no children, right? So this is not a leaf. This is a leaf. So this only has 2 leaves. And what's the total number of leaves? It's in the sum, right? So number on the left plus the number on the right. And what's the base case? Well, how many leaves does that have? Clearly 0, right? So now, is this code going to work? Your base cases are 0. All you do is add. When are you going to get anything, right? That should be one intuition that you got is how do we get our first non-zero number, right? So we go here in our cases and we see, does that work? Yeah, that works. Does this work? Yeah, it works because there are no leaves over here. The number of any leaf is here, right? Does this guy work? No, right? This guy works and this guy doesn't work, right? People follow that? So that's why I say you have to work on these very special cases and see what happens. Here's a case that needs something special, right? So we have an additional base case. I still like this base case so that we can use it here, but I'm going to have another base case, right? So in our code, we're going to say if it's the empty tree, it's 1, and if both the left subtree and the right subtree are empty, right, then the answer is going to be 1, right? And that's how we get going. And then from then on, we just sum. Everybody buy that? In fact, what this is going to do is it's going to count. I mean, it's going to count the number of times that this happens, right, from the number of leaves. Everybody good? This one here? This one basically says, am I a node with no children? Right? I could have said that. If I have no children, right, I was trying to be a little bit, my left subtree is empty, my right subtree is empty, then I have no children, so then the answer is 1.
And what about that just if it's a null tree?
If it's an empty tree, if there's null tree, right, exactly. If I'm not even me, then the answer is 0, right? Everybody good? Here's our traversals. A couple people have talked about traversals. So if you want to traverse the tree, and every time you get to a node, you want to do something like apply max to it or whatever it is you're wanting to do there, then you need to go through the tree. And the difference between these is when do you do the action? All right? So a prefix is you do the action on the root, right? If we're printing them, we do the action on the root, and then you recurse left, and then you recurse right. So here, if we're doing this tree here, you do the 5, and you recurse. You say 3. See how I'm tracing this out? You say 3, and you recurse. You say 1, and then you don't recurse, right? And then you come down and say 2, and 4 and 5, right? Over here you say plus, times, 3, 4, 7, right? Right. So the other order is postfix, where you recurse left, you recurse right, and then you visit the root, right? So here we recurse, we recurse, we recurse, we recurse, we say 2, and then we say 1. And then we say 4, then we say 3, and then we say 6, and then we say 5, right? Here, you recurse, you say 3, 4 times 7 plus, right? And when calculators first came out, I know because I was a teenager, they came out as, and they called it reverse Polish notation. I don't know why they called it reverse Polish notation, but that's what you did. You would type 3 enter, 4 enter plus, and then you would type 7 enter plus, 3, 4 times 7 plus. That's what you would say on the calculator. Yeah?
Are we going to use recursion only with trees, or are we getting into something else too?
We're going to have lots of examples in recursion. All right, so what's infix is when you do it in the middle. You recurse left, you say the root, you recurse right. And you see, so here we're going to go recurse, nothing, 1, 2, 3, 4, 5, 6. And this is the natural order here is you're saying 3 times 4 plus 7, right? And is this always going to give something that reads accurately? No, because sometimes you need brackets, right? Here it happens to work. But if we reverse the times and the plus, then it wouldn't read accurately. And that's, in fact, why the calculators initially made you do reverse Polish notation, because they didn't really figure out how to do brackets yet. Everybody got that? Okay, now, if you have a big tree structure, right, A's pointing at this big tree structure, and you say B equals A, then what's B? It's pointing at the same tree structure, right? We haven't actually copied it. So if you want to copy it, so here's a program where you pass it a tree, and what it returns is a pointer to a brand new tree. That's a new copy, right? So if you pass it the empty tree, which is a null, then what you return is the null, right? Otherwise we take the root and we allocate memory for one node, right? And we copy all the information that's in the root over to our new node. And then we recurse on the left, building the tree, and then we have the copy of our new node, right, be pointing at what's returned here, right? And then we recurse on the right, and we get our copy. The right subtree of our copy is going to be what's returned. Yeah?
So there's no pointing in this example. It's just making new copies of each side.
Yeah?
Adding it to the copy page.
Yeah. No pointing? What does that mean?
Yeah, so there's no, are we doing pointers or no pointers? So are we copying the data and storing it into...
Oh, this is, yeah, we're copying the entire tree, but there's lots of pointer manipulation. This is returning a pointer.
But in the end, we're not, the copy here is not pointing...
No. The whole point is to make a new tree. Everybody buy that? And if we want to deallocate the tree, right, in Java, they have garbage collection. But if you're doing C, you don't have garbage collection. So how do you clean up the whole tree without dropping it? Right? You say, well, if the tree is not empty, then you can deallocate the left subtree and the right subtree and deallocate the root. Right? This is a recursive call. These are recursive call. And here you're doing whatever program thing you do and you clean up yourself. Yeah?
I was just wondering, what happens if we deallocate the root by itself?
Then you draw here. In fact, it's funny that you should say that. What happens if I put that line first? Then the root's gone, but you've dropped all their children.
It's not possible.
It's possible, but it's called garbage leaking, memory leak. It's a memory leak. Right? Yeah?
If you do that, you would have two subtrees and they won't be deallocated.
Yeah, exactly. Memory leak. Right? So here we don't want to drop the children, right?
So if you wanted to create like two separate trees for one tree, we could deallocate the root and have two new pointers.
Yeah.
Okay.
Yeah, you would have to do that. All right, drops the tree. All right. All right, so now we're doing binary search tree, right? And remember the rule, we're given a binary search tree and a key that we want to find. And what do we know? We know that for every node, everybody in the left is smaller or equal to, everybody in the right is bigger than and equal to, right? And before we did an iterative algorithm, right? In the iterative algorithm, I had my finger on one of the nodes, and the loop invariant was that if what I'm looking for is anywhere, it's in this subtree, and then I compare with the root, and I move my finger left or right, right? That was an iterative algorithm. Now what do I do? Oops. Right? Now, right, my postcondition, if the node's not anywhere, then it could tell you not anywhere. But if it's there, it returns something appropriate. Right? So here, what do? Well, if my tree is empty, then I know it's not there. Right? So I return the key's not anywhere. Right? And otherwise, if I have a root, I compare the key to the root, and if the key's smaller, then I search the left subtree to find the key, right? And you'll note whatever my whatever answer he gives, I return, right? I never actually even care or notice whether the key was there or not, right? The friend might be saying it wasn't there. The friend might be returning the data, right? Whatever my friend says, I return the answer, right? And similarly, if it's on the right, and if it's right, if the key is the root, then I somehow return the data to root. Yeah.
Why don't we put this middle outlet in the beginning? If that's the key, you don't have to search the left subtree.
Well, it's only going to do one of these. It's
Oh yeah, that's not true.
it's only going to do one of them, right? Right. So how many? I mean, if you're asking the running time of this, right? Does it do the whole tree? No, it only has one friend. It's still only following a path down one way, right? And you might not have, you had to catch that actually it only recurses once. Right, everybody good?
Log in running time? Does it only follow on one path? Or?
I would say on a 2011 test that the running time is the depth of the tree, which hopefully is log n, but might not be, right? We never said this was a balanced binary search tree, right? If we made it an AVL tree or a 2-3 tree or a red-black tree, then we would get it balanced.
You just said it's search BSE.
I said it was a binary search tree. I didn't say it was balanced. The B is binary, right? Everybody good? How are we doing? We have 6 minutes. Excellent. My sense of timing isn't all that bad.